here. If you haven't done it yet, if you don't have it, I still have some here, but they're on the website. The one on the corner, yeah. I highly recommend you spend whatever 10-15 minutes going over this. There's a solution set on the web, on my website already, so you can take a look. When you're done, you can check. Did anyone who did any of this have any questions about it? Any questions? Okay. We also, that was the first part, there are also some graphs I asked you to do. And I'd like to go over how one would do these. These are a little simpler than what was in the homework, but let's just take a look. The first one is just the tangent of x with a vertical displacement, d, right? d equals 1. So one kind of sneaky way to do this is to just by sneaky I don't mean bad. I just mean it's actually kind of elegant, right? Because you just draw, drawing your tangent function. You might want to label where the asymptotes are. I guess they're at what? Anybody? Where does the tangent go haywire? Where does it go off the map? Cosine is 0, so that's it. Pi over 2, and negative pi over 2, and I guess I didn't. That's really where it is, right? Right. And say, all right, well, if d equals 1, I'm just adding 1 every point. Well, kind of an elegant way to do it is to just draw this and then erase the axis and redraw it at 1 lower. That's kind of a quick and dirty way to. Does everyone see why that works? In other words, you either move the function up 1 or you move the axis down. Right? It does the same thing. So, okay, so that was the first one. Second one, secant of x over 2. Well, let's try and draw a secant here, and we're going to try another little sneaky, elegant way to fix this. The secant is 1 over the cosine. So it might help to start by drawing a cosine function. So that's going to go from 0 to 2 pi. It's going to have its minimum at pi, and so it's going to cross the axis at pi over 2 and 3 pi over 2. And since that's where the cosine is 0, right, that's where the asymptote has to be. That's where the function's going to go off to infinity. And, of course, that'll repeat over here, too. Okay, so this is the cosine function, but we want 1 over the cosine function. So that's the reciprocal, and it's going to kind of look like this. Maybe I should too late. Draw it in a nice bright color that doesn't show up over black. Okay, but the problem we wanted to solve was secant of x over 2, well, that means that the period or the frequency is going to change, right? How is the frequency or period going to change? If this is our b value, remember? You know, function equals a secant of b times x minus c plus d. B is 0, a is 1, c is 0 here. It's nice and simple. But b is now a half, right? So what's our period going to be? How is our period affected by that half?
Pi? Or p?
Well, the regular function is 2 pi, and this is that counterintuitive change. If b is greater than 1, period gets smaller. If b is less than 1, period gets greater. So it's going to get greater by a factor of 2, or we're going to divide by 2 pi by half. It's going to become 4 pi. So the elegant but sneaky way to do this is just change the labels on the axis. This becomes 4 pi, becomes 2 pi, becomes pi, and then 3 pi. So kind of a simple, sneaky way to do that. Okay, and then there was one more on this sheet. The cosecant of x minus theta. All right, so here we have our a is 1, our d is 0, our b is 1. We just have a c, right? So again, I'm going to try this kind of sneaky technique here. The cosecant is 1 over the sine. So let me draw in a sine function. I don't like that. Let's start over. By the way, I encourage you, when you do problems like these, to check them with your calculator. I mean, we want to teach you the intuition and how to do this, but there's no reason you shouldn't use the technology to see if you got it right or not. When you do check with your technology, always remember that if they're not the same, there are 2 possibilities. One is you did it wrong, the other is you didn't get the technology to give you the right answer, right? Okay, so try again here. The sine function. The asymptotes, of course, are where the function crosses the 0 axis. And that let me do it this way. Okay, so that's just the cosecant function. But now, this is shifted, right? Shifted, obviously, pi, but which way is it shifted? To the right. I heard that. Well, one way to shift the function to the right is, you get the, this is 2 pi, and this is pi. One way to, again, kind of a sneaky way to do it is to just shift the axis over pi. Right? So this becomes 0. This becomes pi, this becomes 2 pi, this becomes 3 pi. So that's another way you can thread this needle. All right, are there any questions about that? The next question is homework. There was a homework assignment where you were asked to do this. Are there any questions on that assignment?
Can you just show us number 40?
What was the page?
185.
87.
Regarding the graph that you draw, how do you establish which way it went, to the right or to the left?
You mean the shift?
Yes, the shift, or the phase shift.
Okay,
How do you do that?
if it's a minus,
Uh-huh.
it's a shift to the right.
Okay.
If it's a plus, it's a shift to the left.
Okay. Thank you.
All right, back to, where are we with the homework question?
587.
587, which number?
40.
40. You know, I was fiddling around with this earlier, and I don't have that page here. What do I do with it?
You can give this.
I need the page.
Here we go.
You see it? I'm blinded. Well, I don't want yours, I want mine. Thank you. If I can't find mine, I'll take yours, but I'm very good at losing things. You think maybe I put it somewhere at the wrong place? Okay, all right. I will borrow it from you, thank you. Okay, 40, number 40.
Yeah.
Okay, so let's look at this. All right, so write a possible formula. Now, when they say something like that, they're giving you a hint. They're telling you that there's potentially more than one answer, right? And with all these functions, you can see any place you use a cosine, you could use a sine with a shift. Anywhere you use a secant, it could be a cosecant. And the same with the tangent and the cotangent. So what does this look like here? Which family of functions does this look like?
Tangent?
Yeah, tangent or cotangent. It happens to be sloped the way the cotangent is, but we can always turn the tangent around by using a minus sign if we want. All right, well, let's go back to that basic
So it's pi.
form, you know, that basic structure. So, oh, they're going to use theta, of course. So, A times, we'll try cotangent of B times theta minus C times D. Okay, plus D. Well, for starters, we know that D is the midline. And I want to see if I can kind of do this in a nice way. So, so here's my period. Listed here. And we know the cotangent or the tangent is going to cross, normally going to cross the x-axis right in the middle. So, again, I'm going to just fold this in half. I'm going to say, all right, where does that happen? Seems to happen
At 1.
right there at 1. Yeah, that looks like 1, right? So that tells me immediately what? Which of these letters does that let me know?
That D is
D,
1.
right, my D is 1, right? While we're there, that distance,
Is
if you move it over just a little bit, you can see it's 540 degrees, right? 540 degrees. 540 degrees, that's
3 pi. 3 pi.
3 pi? Okay, so instead of the period being 2 pi, if B is 1, it's 3 pi.
3 pi.
which means b has to be
1.5.
less than or greater than 1?
Less.
Less than. It should be a fraction. And what fraction turns 2 pi into 3 pi?
Maybe 3/2 5.
3 halves.
3 half.
3 halves. So now we know my b is 3 halves, right? Theta minus c. Well, c, that's the offset. Well, they're showing you right here. You can see here's 0, and obviously this cotangent is moved this way. How much is that? Well, that's 180, so that's 90. I don't know, your guess is as good as mine, but I'm going to guess 45 degrees. That look like 45 degrees to everyone? Something like about a quarter the distance. Does this help? Looks to be about a quarter the distance between this line.
Yeah.
Does that sound right?
Uh-huh.
And the whole distance is 180, so I think it's about 45. Now the question is it a positive 45 or a negative 45?
Negative.
Positive.
Negative.
Okay, you two go and take out your boxing gloves. If we move to the right,
It's
it would be minus, so if we move to the left, it's positive. So you can either think of it as minus a minus 45 or just plus 45. Okay, we're almost there. The part that's left is,
Can you zoom in? Can you zoom out?
oh, sorry, thank you. All right, so here we are. The only thing we don't know is the A, and what the A is going to do is it's going to affect the shape of this. So, for example, for a regular cotangent, it might, I'm going to try and be artistic here, but, well, actually I'm not. I'm just going to go right and bring up grapher, because that's the way to do it.
3. So it should be 3.
I have to switch over now. Is everybody with me here? Okay, so what have I got here? I've got cotangents of, I'm going to say 1.5, because it's just simpler to do that. X plus 45 plus 1. Now I imagine the problem here is it doesn't know what a CTN is, so I'm going to say 1 over tangent. Oh no, I typed it all in. Type it all in again. So can I copy and paste?
I think we shouldn't use 45 here.
We shouldn't use 45?
Yes.
Degrees, we should use it, convert it
We
to
should
radians.
use
Radians instead of degrees.
This is pi over 4.
Oh, that's true, yeah, this
Yes.
guy isn't going to understand that. You're quite correct.
Let's use a quarter of a 1.
How about,
Sorry.
We
how
don't have
about
pies on
1 divided by
in a
square root of 2? How about that? Well, something's wrong here. Oh. So I've definitely got 1 over the tangents. Let me get rid of this for a second. Oops. Oh, well, it's that plus 1. Plus 1 is in the wrong place. Plus 1 should be here. That's part of my problem.
Потому что у нас нету
Okay, so I think that was the whole problem.
нету пи на графике.
Back.
Компьютер не знает, что
One
такое
divided by
если у него на графике цифры.
square root of 2. I don't know, can you see that on the board? All right, so this sort of looks like our function, doesn't it?
No,
What's wrong?
it's too, so we don't have the, how you call it? The, yeah, so the slope is smaller or bigger? Smaller? Smaller?
The slope just looks really different compared
Yeah.
to the original one.
So we've got a cotangent, 3/2, x.
What is SQRT over 2? So you divide,
Over square root of 2, that's the.
yeah, you divide 1 by
Oh, what
square
am I
root of
doing?
2.
No, I'm brain dead here, I'm thinking too hard.
Yeah, that's
What
not
I mean
right.
is 3.14159 divided by 4. There we go.
No.
No.
Can you do just 1 divided by 4? Just 1/4 plus 1/4.
But it's not 1/4, is it?
It's 1/4.
It's 1/4
Yeah, but we have
of
on our,
pi. Isn't it?
Yeah.
can you try 1 over 4?
But it's not, it's pi over 4.
Yeah, I know, but we don't have pi and degrees on the graph. So that's why computer will not understand this.
I think it's in radians, so I think
It's in
that's
radians?
just what I want. We're pretty close, but there's something wrong here. Where are the asymptotes on this? They're at,
45.
so 540 we said is 3 pi, that's about 9, and it's a little less than that. So what am I doing wrong here? Oh, I'm multiplying by 1.5. I want to divide by 1.5, right? Is that what I said? 3/2. Oh.
Why are you dividing?
Multiplying it by 3, no, that number is wrong. Where did I come up with 3/2?
The period, you divided.
Yeah, that's wrong. Yeah, it's 3 pi. And I want a number less than 1, so that's 2/3. Okay. All right, 2/3, so 2 divided by 3. That looks much better, doesn't it? No, it doesn't look good. It's still not wide enough. So where did we go wrong?
Maybe because you don't have the whole pi in there, you just have the first 5 digits of pi.
No,
Is it?
that's close enough. I'm way off.
So maybe it's the
Okay,
plus
so
1.
it's 3. So I'm looking for a period of, oh, wait a minute.
1.8.
Okay, wait a minute. What's the period of a tangent? It's not 2 pi.
Right?
It's pi. Right, so to go from pi to 3 pi, I have to multiply by 1/3. Okay, so that's a tricky thing that you're going to have to watch out for when you're dealing with a tangent as opposed to either a cotangent, cosine or secant or cosecant. Forgot about that. All right. Okay, this looks much closer, doesn't it? All right. Let me back out a little. Zoom out a little. Okay, this is starting to look like what we're dealing with, right? This is about a quarter of the way, right? Okay. All right, everybody okay with this so far? Okay. So now, what I want to, as I look at the graph over there, it actually looks a little different, doesn't it? Maybe not. It's hard to tell. But the point I wanted to make about all this was the b value. So let's change the b value to 2. Oh, what happens? Changes the shape. Let's try a little more. 4. Okay? Hmm?
Isn't that the A value?
Yes.
It's the B value.
Oh, I'm sorry. Thank you for correcting. Thank you. Yeah, the B value. The A value. See,
The first value.
my mouth isn't connected to the math part right now. Okay, so the bigger I make this A value, what we call the amplitude for a sine and cosine function, the steeper the curve gets. If we were to make it smaller, then it kind of flattens it out. Now, the point I wanted to make about the A value here is if you just have an assignment on a test or a quiz or homework, the only way you would get this shape right is either by using technology, which would be the smart way, or by plotting points. That's how you could get the shape. And I just want to make it clear that on a test or a quiz, I wouldn't expect you to get this exactly right. The worst I might do is I might say, let's see, let's duplicate this. You know, I could imagine asking this question. Duplicate it. No. So if I said, which of these curves is A bigger, right? Is it this one, or is it this one? Any answers? It's this one, right?
Yeah.
Goes up more steeply and down. All right, you might want to keep that in mind. Okay. Any other questions about graphing these functions?
Yes, could you go back to the part where you were writing the formula on the paper, please?
Too early. What just happened? Oh. Wrong button.
What happened to A?
Well, that's what we were just looking at.
Yeah, okay.
Okay, so what I'm saying about this function is that the A is going to affect the shape of this curve. It could be steeper, it could be kind of flatter. And you should know that the bigger A is, the steeper it's going to be. But as far as being able to reproduce it exactly, you're either going to use a graphing device, some kind of technology, or you would have to plot points. You'd have to actually say, well, for 180, where is it? For 90, where is it? That's the only way you could get that shape right. And that would be an arduous and tedious and unimportant task
So we just
to
assume,
make you perform, right?
okay, so we just assume A as 1, right?
For now, if you just said A is 1, that's fine. And if you said it was 2, I'd say, yeah, okay.
Okay.
If you said it's 100, I'd say, that doesn't look right. That would be almost like a straight line. Okay, any other questions about this? Yes?
Hey, can I just see how you entered it on the graphing website?
Oh, on the graph? The grapher, you mean?
Yeah, the grapher, yeah. Thank you.
Okay, I don't, can you see it up there?
I can come.
Let me repeat what let me do this, let me copy it from here. Again, this is not, to me, this is like some obscure area of computer science or using technology. So the function is this line on cotangent 1/3 theta plus 45 degrees plus 1. Well, grapher doesn't do things in degrees. Maybe you can change it. It doesn't seem to have the cotangent function, right? So instead what I have is 1 over the tangent function. For 1/3, I put in parentheses 1 divided by 3. He doesn't deal with theta, he wants an x plus, now 45, is it 45 degrees, was that right? I think that was right. Yeah, for 45 degrees, we have to convert that to radians. So 45 degrees is pi over 4, but again, I don't know if he has a symbol for pi, so I just typed in 3.14159. That's my favorite approximation. 3 digits is probably fine for something like this, divided by 4 plus 1. If you have one of these, don't play around with it. Don't show up and say, how do I do this? Same thing with your calculators. You want to use it on the homework, and if you have some trouble with it, if it's giving you the wrong answer and you can't figure out why, you should bring that question into class, because you may not be the only one who's having that problem. Okay. Anything more about this?
Yeah, it's 41. If it's possible, can you show us 41 as well? Thank
Next,
you.
same page.
Sorry.
No, it's okay. 41 asks,
The same thing.
well, no, it's not the same.
Required.
The same but different. Okay. So here, we clearly have either secant function, which is 1 over the cosine, or a cosecant function, which is 1 over the sine, to deal with. All right, so let's think this through. What does it look more like? Well, it looks like the asymptote is at 0. And that's like a cosecant function, right? Let me just draw here. So here's the sine. So a cosecant is kind of like this. And here's a cosine function. So the cosecant, so the secant is more like this. So looking at these, this to me looks more like secant function, except for one thing, which is it's upside down, right? Where the secant is positive, this is now negative, and where the secant is, and where this is positive, the secant is negative. So I can fix that real easily, right? I can just put a minus sign in front of my secant. That's going to flip it over. Okay, so let's kind of write that out here. So we have some function of theta, which is minus the cosecant. Minus a. Sorry. This isn't a prepared lecture, right? Minus a, where a is positive, cosecant of b times theta minus c plus d. All right, so seems to me the first thing we want to hammer away at is the D value, that's the midline. So how are we going to find out where the midline is? Well, I don't want to write on this homework page, but I'm going to kind of draw this here. So we have this, we have this, and you can see instead of you can't talk about the maximum and the minimum of the function, right? The maximum is infinite, the minimum is infinite. But for cosecant and secant, there's this kind of an empty area, and we can look for the positive area for the minimum, and for the negative area, the maximum. And the midline, the D value, is going to be between them. So as I read this, I'm going to read this sloppy. It really looks like about 3.8, but I'm just going to call this line here 4. And I'm going to call the line down here -1. Is that clear? So the midline is then going to be, the D is going to be 4 minus -1? Yeah. Over 2, which is going to be 5/2. King, did I do that wrong when I was showing it to you? I think I may have subtracted. Anyway, so there's my midline, there's my D value.
You said the midline, right?
Yeah.
Wouldn't it be 4 plus -1?
4 minus
1
minus
equals 3 to 2?
is 5 over 2.
Isn't the max
for the
plus
midline,
another?
I think it's plus.
Yeah, it would just be 3 halves.
Is it 3?
It's plus
3 by
the
2.
-1.
The
Okay,
M,
one person at a time. You
Because-
think I'm still
because
wrong
it's-
here? That's fine.
the formula for the midline is the maximum plus minimum. And then you found the amplitude right now. You use the formula for amplitude,
Let's see.
which is maximum minus.
Ah, you're quite right. Thank you. It is plus. And it is 3/2. Is that what you're saying? Yeah, that's right. Okay, so D is now 3/2. Right, so that's just telling us, we have this function, we're moving it up and down. So now we know it gets moved up 3.5. Okay, that takes care of D. By choosing the cosecant, does everyone see that we've made C equals 0? Now, if we chose a different function, or this was off a bit, we might have to adjust C. That's the phase offset. But by choosing the cosecant here, which would start here, we just had to multiply it by a -1 in the front. But our offset is 0, so our C is 0. So we have D, we have C equals 0. How are we going to find, well, let's go after A, right? So A is kind of like, let me describe it this way, it's kind of I'll call it the empty amplitude, the amplitude of the empty space here. Right? In other words, if I drew in my cosine function here, or my sine function, right? If A gets bigger, the sine function gets greater, and then the cosecant function gets further and further away from the midline. So what is this distance here? Well, it's what we did before. It's 4 minus a -1 over 2. So that's, I'm not going to get that right, am I? Yeah, it is, it's 5/2, yeah. It's kind of the same thing we were doing with the sines and cosines when we were graphing them, except now it's not the size of the sine and the cosine function, it's the space that it would take up. All right, we're almost there. How do we find the b? What do we have to look at to find the b?
Period.
The period. So what's the period of this function here? It goes from 0.
Pi half? No.
Oh, no, I'm not. I just noticed that the little red lines, the asymptotes, are actually offset. So my c is not actually 0, is it? All right, we'll fix c in a minute. Is my head under the
Yeah.
there now? Yeah, I've never done that before. Okay, so what's the period? What period is pi? What's the period if b is 1? No, it's 2 pi, right? It's like the sine and the cosine. Right? So in order to take the period down from 2 pi to pi, what do we want to do with b? 2, yeah. So b is 2. Okay. Now, I guess we can go in with a fine-tooth comb here and adjust c a little, right? So it's moved over, I'm going to zoom in. There it is. Everybody see that? Kind of zooming in this little distance to the left. Right? Since it's going to the left, are we going to be subtracting a c value or adding a c value?
Adding.
We're going to add it. And someone want to tell me what they think that distance is?
Yes. Not like
Yeah, I
this.
think it's about 1/5 of 90 degrees, right? I mean, that's my guess. You can guess a little different. You can say 1/4. It's not a 1/3. It's not a 1/10. All right, so 90 degrees is pi over 4. So 1/4 of that would, 1/5 of that would be pi over 20. Yeah. Okay, so c is close to 0, but we're going to call it pi over 20. Oh, zoom out. There it is. C is pi over 20. All right, let's just write the answer, because it's always nice to see what the answer actually turns out to be. All right, so our function of theta is negative 5/2 cosecant of 2 times theta. Should we write that pi over 20 as degrees? Since the whole thing is in degrees, we probably should. So pi over 4 is 90, 1/5 of 90 is 18. Plus 3/2. Okay. That's a lot of work, isn't it? Okay. A lot of places to make errors too. All right, are any questions about this? Yes.
Should it be plus 18?
Oh, thank you. You see, there are plenty of places to make a mistake. All right. And any more questions? Graphing. Expect to be required to graph something on the next quiz.
Do we have quiz on Monday?
Hmm?
Do we have quiz on Monday?
Yeah, these quizzes, they just
Every 2
about
weeks?
every 2 weeks, you're going to see. After that, we're going to have the midterm. Gosh, this is travel fast. But we're only halfway there, so don't It's the quarter term, not the midterm. We're at. Okay. Let's turn this. So, before we go on today, well, as we go on today, I want to do a little review of something having to do with functions. Namely, I want to talk for a minute about inverse functions. I assume in either the 48A or B you talked about these. Has anyone not run into an inverse function before? Okay, well. I'm also, I'm going to give you something, we'll call this supplemental. That's a nice way of saying it won't be on the quiz. But I want to give you a little better appreciation for how math works. Because I'm going to talk about functions in a little more abstract way. I think everyone's used to the idea that, you know, function could look like this, f of x equals, and then, you know, we have some other function. We're working with sines and cosines, but it could be like a polynomial, something like that. This is a function, or rather, this is a way of describing a function. We're using a little shortcut here because while I describe the function, I describe how you figure out what the function is. I didn't tell you what the domain was. So you probably just assume the domain is all real numbers. And then from there you can figure out what the range of the function is. Anyone so sharp they can immediately see what the range of this function is?
All real numbers.
It's not actually.
From 0 to infinity.
From 0 to infinity.
0 to infinity.
That's close. It's close. What happens if I put in minus 0.1?
It'll be
It's going to dip a little bit. This is a parabola. I don't remember where the bottom is. We can figure it out, but we're not going to do that today. Okay, that's the way you usually think of a function. In mathematics, we define a function a little more abstractly. Before I tell you what a function is, I'm going to describe something even more general called a relation. So what a relation is you have two sets, set A and set B. Do you know what a set is? It's a really general, it's a collection of something, right? All the functions you've dealt with have dealt with a relation between A and B, where A and B are numbers. But a relation can be between other kinds of objects. So we can have some numbers in our domain, and we have another set, which in this case is also going to be some numbers. And then we have a mapping. And you can think of this relation as the two sets and the mapping between them. So I'm going to map 1 to 1, and 3 to 2, and 4 to 4, and I'm not going to map, well, I have to map 2 somewhere. I'm going to map 2 to 2 also. So here, my range is just 1, 2, and 4. 3 is not part of my range. So that's a relation. The thing about a relation is we could have 3 also go to 3. 3 goes to 2, and 3 goes to 3. And that's not a function, right?
It's not inverse function.
We're not even there yet. We're not even to functions yet, right? Okay, so let's see if I have a little better picture here. Show you, should. Okay, so here's my picture of a relation. Okay, so this is not a function either. This is a relation between a set of letters and a set of numbers, but it's not a function. All right, why is it not a function? Because z goes with 2, 3, 4, yeah. It fails the horizontal, there's no real horizontal line test here, but that's the problem. Now, if we take a relation and we get rid of these problems here, right? So now, each member of our domain just goes to one member of the range. Now we have a function. In this case, the domain is finite, but most of the domains you're dealing with are infinite. And again, the function is these sets and this mapping between them. Okay, that's a function. This is now a function. We're going from x to y. But it also has an inverse, which we often write f minus 1, which does not mean reciprocal, right? It just means inverse. Now, in order for this to work, for us to have an inverse of our function, what we need is what we call in math a one-to-one function. That is, a goes to 1, 1 goes to a, b goes to 2, 2 goes to b. Everything in the domain goes to something in the domain, which then goes back to the same place in the domain. One thing you might want to notice is that for the function x is the domain and y is the range, but for the inverse they flip. Now y is the domain for the inverse function, and x here is the range for the inverse function. Okay, sometimes we can take a function which doesn't have an inverse. Let's take a look at this. Here we have a goes to 1, c goes to 1, b goes to 2, and d goes to 2. Now, if you want to look at the inverse function, we've got a problem. The problem is 1 goes to a, and 1 goes to c, 2 goes to b, and 2 goes to d. That's not a function. But sometimes we can take this and we can fix it. We can do that by getting rid of c and d. Now a goes to 1, and 1 goes to a, b goes to 2, and 2 goes to b. So we truncated the domain so that we will have an inverse function. Now, I know that's pretty abstract, but we're going to do it in a very practical way shortly. Before I get into the trig functions, which is what we're really going to deal with here, the inverse trig functions, I want to show you some things you may be aware of. Okay, here we have, first we have a nice simple function that's a parabola. That's our f of x equals x squared. And if I want to make that an inverse function, I have to be careful. See, 0 goes to 0, 1 goes to 1, minus 1 also goes to 1, right? Here's 0, here's 1, here's minus 1. They both go to 1. So if I were to look at the inverse relation, it's not a function, because now I have 1 has to go to 1 and minus 1. So I'm going to fix this by restricting my domain of x squared to just 0 to infinity. So I get rid of this branch of the parabola, and now I can have an inverse. What is the inverse of x squared? Well, it's the square root of x. And I've graphed them both here. All right, here's my x squared, here's my square root of x. And I want to see, are people familiar with the relationship between these two functions I've graphed here? Does everyone see that if you draw this line here, y equals x, that they're the mirror image of each other? This is a very, very, the more you think about this relationship, you know, the better. Another way you may have seen the same idea is, let's say someone gave you some function, we'll say, you know, y equals e to the x. Everyone's familiar with y equals e to the x? One way to find the inverse of a function is you switch the x and y, right? Giving us x equals e to the y, and now you solve for y. Does anyone know how to solve for y here? Yeah. Log, find the log of both sides. So we have the natural log of x equals the natural log of e to the y, which is just y. So I have y equals the log of x. And if I graph these two functions, I will see that they're mirror images of each other along this line y equals x. Okay, that's our introduction. Now let's get down to kind of the brass tacks here. Here I have a sine function, and I want to find its inverse. So again, I'm going to look at the mirror image across y equals x, and it kind of looks like this. Well, immediately you can see we have a problem here. This is not a function. Okay, how can we fix that? How have we been fixing relations that weren't functions and
Restricting its range?
restricting its domain? Exactly. I'm getting a little cold. Okay. Excuse me. All right. So this is how we truncate the domain. All right. We restrict. Oh, did I do this already? No. Go back. We take the sine function and we restrict it between what? Well, we have to restrict it between negative pi over 2 and pi over 2. And now our inverse is now, I'm not drawing this very well, our inverse relation is now a function because it can now pass the vertical line test. Okay, that gives us an inverse function which we can either write as, sometimes we write this as arc sine of x, or sometimes we'll write it this way, sine minus 1 not meaning reciprocal, meaning inverse of x. Okay, so this is what that function looks like. Let's take a look at it. Its domain has to be between minus 1 and 1, right? The range of the sine function is minus 1 to 1, so the domain of its inverse function is minus 1 to 1. And its range goes from minus pi over 2 up to pi over 2. Again, remember we truncated the domain from minus pi over 2 to pi over 2. So now the inverse function, the ranges and the domains are going to switch on us. All right. Okay. So here's another way of looking at it. If you think of the unit circle, the sine function is what? It's the y coordinate, right? So as we go from minus, this is minus pi over 2, back up to pi over 2, this coordinate is going to go up and down here between what? Minus 1 and 1. So that's another way to think of the inverse sine function. We're gonna do some more with this. I want to mention one more thing before we go on break. That particular restriction I described of the domain is arbitrary. You could choose another domain, right? But let's use this term. It's the standard way it's done. And in particular, you're going to find on your calculator that when you use the inverse functions, it's going to use that standard restriction. So let's look at what I mean by that. Let's first check our mode. I'm just going to go to degree mode for the moment. And to get your values of your inverse functions, again, if you take a look here, go up a little, on the sine function, each of these sine, cosine, and tangent, there's a little blue thing here, sine minus 1, cosine minus 1, tangent minus 1, again, inverse, not reciprocal. So if I say second sine, and I say 1, it's going to tell me 90 degrees. That's pi over 2. If I I'd say second, say minus a half. Okay, that's minus 30 degrees, right? All the numbers you're going to get out of this function are going to be minus 90 and 90, or minus pi over 2, pi over 2. Now, if you think about it, these are not the only numbers whose sign will give you these values. Right? Because there is, well, I better stop talking. We'll come back, we're going to do some more of this. Take a break for, say, 10 minutes.
Oh,
See here.
did I give you that? Or I didn't say that. Did I say that?
That's me.
Oh. Okay. Oh, sure. It's just that I remember that. It's just that. There's one more reason for not acting.
Sorry.
You can take that now if you want. You haven't handed it, but it's okay. You can take it.
It's not my fault. Just know me from the
Does it look better from here? Take it.
That's not a hand, that's my notes.
I mean, I haven't seen the. Can you read it?
Okay.
I just came off this. You have to go all the way around. He told me that you are
Is it? Isn't it too high?
It's too high? What do you want to make it?
That's
Anyway.
yeah. Oh. Put it down a bit. Up. All right. That's good.
Okay, everyone. Can we come back to focus here?
Do you think you're going to be good?
Probably, actually.
We're missing somebody.
Going to noise concept.
What concept? Oh, you have the same one.
What's that? The brand new?
Okay, can we listen up again? Okay, so this is the kind of related diagram for the cosine, the inverse cosine. The cosine, of course, is the x-coordinate going around the circle. And this is how we truncate the domain of the cosine. Instead of between, for the sine, it's between minus pi over 2 and pi over 2. You can see here for the cosine, we're going to truncate it between 0 and pi, so we can get an inverse. And this is what the inverse cosine function looks like. So again, its domain is going to be minus 1, between minus 1 and 1. But now its range is from 0 all the way up to pi. Again, this is the standard way of truncating the domain for the inverse, for the cosine function. And it's the way your calculator is going to work. Let's just take a look here. Let me put in, let's say, inverse cosine of minus 0.9. Okay, so you see, that So what is that number? I'm in radian mode, right? So if I divide that by pi, well, I divide it by pi and multiply it by 180, I get degrees. Again, as I was, when I was discussing the sines and cosine functions, you have to be careful about which mode you're in. In the case of the inverse functions, your input isn't going to change, but your output will. So if you get a funny looking number, if you were to get like a large number like this and you were expecting a number between 0 and pi, well, then you just want to look at your mode and see what your mode is in. If I change to degree mode here, you'll see that if I again say cosine of minus 0.9, then I get 154 degrees. So again, the output from the calculator is going to be using this standard method of truncation. Okay, we're missing one more major function. That's the tangent function. This is what the inverse tangent looks like. Remember this idea of reflecting it across y equal x. There's our tangent. So our inverse tangent kind of lies flat like this.
What about other part of tangent that are going to minus x and infinity?
You mean the ones over here?
Yeah, they will
Well, see, what I have to do is I have to truncate, to get an inverse, I have to truncate the domain. So I've now eliminated this. This is like my truncated tangent function.
be. Yeah. So other part will be split.
Well, they would
y-axis?
they would be at a different level, but if I don't truncate, then I don't have a function. I have multiple values, right? We're going to get to, I think I know what you're getting at, which is there are, these are values for the tangent, right? But there are other possible outputs to the tangent, inverse tangent. Just hold on to that thought for a second. We're actually, we're not going to do that today. We're going to do that Wednesday. All right. Let me see if I can just explain real nicely what we mean by that. Let's take the sine function for a second. So, let's say I were to say, I want to know what the inverse sine of 1 is. So using my standard, there's 1. Using my standard truncation, the function is going to give me this value pi over 2. But that's not the only number whose sine is 1, right? I can draw a horizontal line here, and I'll find that 3 pi over 2, is that right? Yeah, 3 pi over 2, and then I think this will be, no, these are gonna differ by 2 pi. So pi over 2 plus 2 pi, and pi over 2 plus 4 pi, and pi over 2 minus 2 pi. Those are all numbers whose sine is going to be 1. So we're going to talk about that on Wednesday. Again, we're not talking about a function anymore, we're talking about a relation, right? where there's one input and many outputs. Okay, so I haven't confused the issue too much here. Here's my inverse tangent function, looks like this. So its domain is what? This is not the truncated domain of the tangent. This is the domain of the inverse tangent. What's its domain? And what values can I plug into the inverse tangent? All real numbers. Negative infinity to positive infinity. Now, what is its range? Right? What values does it go between?
Negative 2 to 2.
I'm hearing the 2, I'm not hearing the rest.
Yeah, from negative 2 until 2.
From negative 2 until 2. Well, it looks like that almost on this graph, but it's not. Okay? The way to think about it is, think of the tangent function. It's between these two asymptotes. Where are the asymptotes?
Pi over 2.
Pi over 2 and minus pi over 2. So its range is minus pi over 2, pi over 2. And you'll notice this is what we call an open interval. It never reaches minus pi over 2. Right? Notice if you plugged in a bigger and bigger number, you'll get closer and closer to pi over 2. Smaller and smaller number, you'll get closer and closer to minus pi over 2. Okay, that's the inverse tangent function, or the way we create it by truncating the domain. And again, that tells you the values that your calculator is going to provide for you. Let me double check here. I want to go back into radian mode. So let's just check what I just said. If I say the inverse tangent function, let's put in some big number. All right, what do we expect? What do we expect this to be? Right? As I pick a big number way out here, right, it's going to get closer and closer to pi over 2. And that's exactly what you see here. All right. Okay. Let's look at some problems. I'm going to start with a very simple one. Find the angle whose sine is 1 over the square root of 2. Okay, so we're looking for some angle that whose sine, its y value is 1 over the square root of 2. Well, you should identify that immediately. That's our isosceles right triangle. The angles are what, 45 degrees or pi over 4. Okay. Are there any other values whose angle, whose sine is 1 over square root of 2? Well, this is positive and we're in the first quadrant. Where else is the sine?
125.
Okay, 100 and,
Oh,
not 125.
oh, I said wrong. 225. Sorry.
Wait, 225, that's going to be down here, that's going to be negative,
Oh,
right? That's negative, negative, right? This is positive, positive, negative, positive, and positive, negative. So the question is, where is the sign, that's the y, also positive? It's going to be positive here. Yeah, another way to look at that is if I draw y equals 1 over the square root of 2. That's this line. It's going to intersect over here, and that's, of course, going to be 3 pi over 4. All right, so we've got starting to get a handle. Here are 2 possible solutions. How can we get some more solutions? Yeah.
More angles? You mean?
More angles whose sine is 1 over the square root of 2.
Add 360.
Okay, except I don't want to add 360. I want to add 2 pi. And I can really add any multiple of 2 pi, right? So it's 2 pi n. And likewise, I can take 3 pi over 4 and add 2 pi over n. And if I just say x is equal to, where n is a member of the integers, you don't have to use this kind of notation, but that gives me the complete set of all solutions to this problem. The problem being, find the angle whose sine is 1 over the square root of 2. All right. I guess we're at that point where I'm going to hand out a worksheet that has a few problems. Okay. I'm sorry? Oh, you've already got them?
Yeah.
Oh, okay. Want to pass those back? This is going to be easy today. You can pass them. So let's take a stab at these. Let's see what we got. I'm going to ask, I'm going to show total ignorance here. Does anyone know why half the class is gone? I mean, you know, Super Bowl night, Sunday?
Totally. I don't know.
Nobody? Okay, I just,
Maybe they feel cold.
I'm cold.
No, the weather getting cold. So
Oh,
go
okay.
sleep early.
That's so kind. I thought, you know, you could say you're boring them to death. Or, I don't know. All right.
Probably sitting in a car somewhere.
If we go to school, that's for fun.
Okay, I just, you know, I mean, you guys are adults, and I assume you're looking out for your own best interest. I just don't always, you know. I was a student not that long ago, you would be shocked. And I always came to class unless, you know, an alligator bit my leg off. That didn't happen very often. So, and you know, I'd be there the next week, you know, limiting. All right, work on this for a few minutes, I'll be right back.
Yeah, put it on the. gonna get this one and you're gonna get the other one on the other side. So they might wait. How did you get the other one? How did you get the first one?
So
Because, we're looking, it's actually pi.
You know, I mean, how do you do it manually? I know how to do it in college.
Oh, yeah, how do you do that?
Manually, like on papers.
You can graph, and then.
I graph, but how are we gonna know it's a zero?
So, this is zero.
This is a zero?
That's zero,
Okay, and
that is zero, and that was zero. So those are your answers.
you see, no, no, I get it.
All possible. Something like that. I'm not disagreeing, I'm just. I'm not thinking yet. All right, anybody having severe problems with the first one? No? Okay, everyone gets that it's find all the possible values, right?
This one using, use degree or radius?
Don't matter.
Doesn't matter, but I'm gonna switch to degrees. This one, the degree.
That's your, yeah, so, let's say it wasn't this, let's say it was like, you got a third. And so we kind of, okay. Well done, right? This is your word. Oh, it's right. It is correct. It's just that whenever it's multiplied by see how radians are all high. So multiply by
Okay, that's you multiply by number one.
I think that's interesting. You're so, you care about me. Me? Happy feelings. You know? Or happy feelings. Here they are, they're here right now, and is it right? Come on. It's capitalism here. No,
Yes, I'm saying those are
No, it was
actually,
a
oh,
Soviet Union.
maybe,
Here
maybe
it's
I'm not thinking of this all out. The only other thing I would say is, I didn't ask for it, but I do this one exactly.
Got your expression.
Yeah, you could, that'd be a different. Well, on quiz, it might not, it might say do this with a calculator, it might say find an exact, right? There are only a few, those special angles or special sines and cosines that we can do exact right now. Later in the class, there will be more you can do likely, but not infinite numbers, right? So,
Yeah, they physically go around the circle. Sure. So I'm gonna go into show us. Can you go through it fast?
go through what fast? Well, we're gonna go over them, yeah.
I said yes, because which one you have a problem with?
Okay, so everyone completed number one? It doesn't have a number. The first one, everybody done with that?
Yes.
Everyone have an, at least, you beat your head against it a little? Okay. Let's take a look at this. One way to look at this is just to think about the sine function. And this is saying, what are the angles, what are the thetas, where the sine function is 0? Well, you can see it starts at 0, and then every pi interval, it's at 0, right? So pi n.
Can you just put pi n for an answer?
Yes, yes. If you say pi n, I will assume n is an integer, unless you say otherwise. If you say n equals, 0, 1, 2, 3, so forth, I'll assume you mean the positive, 0 and greater integers. But if you don't say anything, I'll assume it's all integers. And if you said this, then I would say you're missing a whole bunch because minus pi, right, continues on in this direction. Okay. Everyone done with number 2? No, okay, all right. And I was mentioning to Peter that I don't say here whether I want this exact or not, but so you could just kind of plug that into your calculator. But you could figure it out exactly. And, it's kind of a good knee-jerk reaction when you can do something exactly to try it. But unless I tell you on a quiz exact, you're free to punch buttons. Yes, that does. But as I said, I'm not that smart. Well, yeah, no, I mean, this is correct, I think, yes. The cosine of minus pi over 4 has to be minus, yes.
Because those are like only two. I mean, that's the only one.
I'm just not sure. Oh, I see, but because you're using pi, yes, I think that's.
Yeah, I think I'm missing something.
I have to.
Yeah. I'm moving slowly.
And I'm gonna, since I haven't figured it out before, picture here. Say, so Peter, you're saying definitely here, right?
No, well, no, there's another one
And the
Okay.
third one.
here.
Where else, so where else is the cosine negative?
In the
The
second,
second quadrant?
yeah, and the third.
Okay. Yeah, so I would say your answer is absolutely correct.
It's one of the correct ones.
No, you put an n after the pi,
Oh, yeah.
then you've got them all. I mean, there's other ways to express it.
Oh, right, yes.
Okay. All right, has everyone at least gotten this far with the second one? See, where is the cosine negative? It's negative in the second quadrant and the,
And the third one.
uh-oh. I talked myself, I do that a lot, I talk myself into the wrong answer. Wait a minute. Oh, uh-oh. I told you wrong.
No, I didn't.
So the cosine, okay, so these are where the negative 1 over square root of 2 is, right? Okay, so this is, what? What's that angle?
135?
Yeah.
135.
Okay, or 3 pi over 4. Yeah, I jumped to a conclusion there. I was wrong. So it's 3 pi over 4, but it's going to be at that spot every time it goes around, right? So plus 2 pi n. And then there's this angle, which you could either think of as minus 3 pi over 4, or you could think of it as 5 pi over 4 over here. But that also every time you go around, so 2 pi n. Okay. All right. Let's think about where is the tangent positive? What quadrants?
First.
Oh, actually, let's answer this question first. What angle in the first quadrant gives you 1? 5 or pi over 4. Okay, so what quadrants is it positive in? Obviously the first quadrant. And the third, okay. All right. Now, in this case, in the case of the tangent, we're going to be able, instead of needing 2 expressions, we're going to be able to express it as 1, right? Because it's going to be pi over 4 plus 2 pi n, but also, what's this angle way over here? That's 5 pi over 4 plus 2 pi n. But if you stare at these close enough, you realize this is just the same as pi over 4 plus pi n. See, they're, halfway across the circle is just pi across, is just pi apart. Okay. Next question. Has anyone worked on this thing, or did they just think it wasn't important? Find the domain needed for secant of x so that its inverse is a function. Well, there's an obvious trick here. You realize that the secant of x is what? Secant of x. 1 over the cosine of x. So the same truncation is going to work. Truncation for the cosine was what? So that's going to work for the secant also. Let's draw that so we see we're not crazy here. So the cosine from 0 to pi looks like this. So what is the secant look like? Kind of looks like this, like this. Now if I reflect this, right, along the x-axis, what happens? I want to go back and look. Now it's getting complicated, right? So it's going to look like, can't do it. I just can't do it. Why don't we cheat? Make life easy. Okay, does this thing have, I don't know if it has an inverse function. Inverse, no, it's not.
I can't see anything, by the way. We don't.
Oh, why do we not? Oh, my apologies. Better? Well, now we're fighting with technology. This is something I'm really good at, but not remember emotions. I think,
Scott, have you ever used
let's try the other method. Oh, Google. Grapher inverse.
You just do one over at a time.
No, that would be the reciprocal. I'm glad you mentioned that, because that's a common, how could mathematicians make the issue more confusing? All right, everybody, burn this into your head, what I'm saying here. The inverse sine function is not 1 over the sine function. There actually is a function where the inverse is the reciprocal. Think about that for a minute if you want.
Will it be sine x in power of minus 1? Sine x in power of minus 1.
Well, that's what this is, right? But these are not inverse functions, right? That's what I'm trying to get. This is not the inverse of this, right? This is a special function. Let's see. Well, look at that, look what came up, right? How do we put a function in here? Isn't this that, oh, I see. Let's see, they have functions. Here we go. Okay, so what did we want? The arc secant function? Okay, so there you have the inverse secant function, right? It has the same range, right? As we use the same truncated domain, which is from 0 to, does everyone see this? From 0 to pi, that's this distance here. Let me put the inverse cosine function in too, because that might make it clearer. Inverse sine of x. How did I do that? Where did I get that function from? Totally lost. Here? No. Well, I need the technology again here. Oh, I could just say arc cosine x. That'll do it. Okay. Oh, so that's very pretty. So we've truncated again. This isn't the sine and cosine. This is their inverses, right? Which are just swapped. You know, they're just reflected along the x-y axis, and we're using the domain of sine and secant function from 0 to pi, okay? And the ranges are complementary. The range of the arc cosine is from, I'm sorry, not the range. I mean, the domain, wait. I want to say this right. For the sine, for the arc sine, the domain is from -1 to 1. And the range is from 0 to pi. The arc cosine has a domain which is greater than 1 or less than 1. Nothing in between, that would be undefined. But its range is the same, almost. Look at that. In other words, this red line here, it goes from 0 up to what? Pi over 2, and it comes down from pi to pi over 2. The ranges actually are a little different. They're missing a hole, right, in the center here, right? The arc cosine has a value, it reaches pi over 2 at 0. But these guys, they would have to go out to either positive infinity or negative infinity. I think what I'm saying is really confusing, isn't it? I mean,
When you're using the wrong graph to represent the question asks for secant, the inverse of secant,
Yeah.
but you have arc cosecant
oh,
and arc cosine.
okay, it says, find the domain needed for secant so that its inverse is a function. So what I'm graphing here is its inverse, which is called the arc secant, right? So we want to find the domain.
Oh, sorry.
Okay, let me go back to the problem. All right, let me go back to the problem here. The question says, find the domain for the secant function so that its inverse is a function. So what I'm saying is, the same domain, the domain we use here is the same as the domain we use for the cosine function when we want to find its inverse. Right? So, looking at these guys for a second, these are the inverse functions. Right? The domain of the sine and cosine that created these functions is this interval along the y-axis, right? In other words, the domains and ranges are switching. The domain for cosine and secant is along the x-axis, but when I flip them, right, now it's along the y-axis. So that this same domain works from 0 to pi. There's one problem in the middle, right? We don't want to use that pi over 2 as part of the domain because the inverse arc secant of pi over 2 is undefined because it's way out here, or way out here at negative infinity or positive infinity. It's undefined. If you can figure this out, you really are on top of things, by the way. And if you're a little confused, don't worry.
Does that mean there's a hole in the blue line?
It's not in the blue line, it's a hole in the red line.